Okay, so for the last talk today, it's my great pleasure to welcome Shipra Agrawal. Very early in the morning, her time on the East Coast, so very thankful that she can make time for us. Shipra did her PhD from Stanford in Management Science and Engineering in 2011. She was in Microsoft Research in Bangalore from 2011 to 2015. And then she joined Columbia University as a faculty in the Industrial Engineering and Operations Research Group. She's she's doing very exciting work on bandits, sequential learning, reinforcement learnings, and many related topics. And today is one of them, dynamic pricing and learning under the BAS model. Shipra.
Thank you, Sandeep. First of all, I apologize for not being able to be present in person there. The conference looked really exciting, and I wish I could be there. And thank you for accommodating my talk online. The work I'm going to talk about today is dynamic pricing and learning under the BAS model. And this is a joint work with my student, my former student, Stephen Yin, and my colleague, Asaf Zivi. The idea here is that we want to look at the dynamic pricing problem, but in a different kind of model. So we want to think about the case where the demand model is not independent across time, and it is affected by something called social influence and imitation effects. And I explain how we model those effects using a BAS diffusion model. And under this model, we consider the problem of how to price the product over time sequentially so that we can, in long term, have a good market share and get a good revenue. And we pose this problem as an online learning and optimization problem, basically in a bandit framework. And we produce theoretical bounds on regret, both upper and lower bounds. And I'll keep the talk informal. If you have any questions, please feel free to ask, and Sandeep can relay those questions to me. So before we move forward, let me just explain what I mean by dynamic pricing. So dynamic pricing is considered a cornerstone of problems in operations management. And the idea here is that, so traditionally, dynamic pricing is one of the major tools used in operations to match supply and demand. So you can imagine in an airline and hotels where you have very fluctuating demands, then pricing can be used to balance them. In particular, if the supply is very high, then you can have a lower price to increase the demand, and when supply is low, you can have a higher price in order to match the demand. Now, when we are talking about learning, then we do not know how this demand is going to fluctuate, and we are going to use data in order to predict the demand. And then we have this trade-off between data and optimization, data and decisions. The key observation here is that now, when we are doing dynamic pricing online and we are trying to learn from the data collected, we are learning from the response of the customers to these prices, which means that the price plays two roles here. It is not only serving as our our point for sales, but it is also serving as a control that decides what kind of data we will collect. So for example, if we have only offered very low prices in the past, then it will be hard to predict if what will happen if we offer a higher price. How will the demand change if we offer a higher price? So now we have this trade-off between a local trade-off between how much information can we collect versus how much rewards can we get immediately. We also refer to this trade-off as learning and optimization trade-off, exploration, exploitation trade-off in learning. And I'm sure, I saw the schedule, and you have learned a little bit about these trade-offs from the multi-arm bandit talks that happened in this conference. So before we move on to the learning problem, let me give a little bit of overview of what has been done in dynamic pricing space and where does our work stand in this space. So there has been a lot of work in dynamic pricing, both from the traditional OR perspective, but more recently from the learning perspective. So from learning perspective, one of the main So from the learning perspective, one of the main model that has been considered is the model of independent and stationary demand. What that means is that every time you offer a price, the demand is being generated from the same fixed demand model. So the demand model doesn't change across time, and it is independent of what happened in the past. And under this model, there has been a lot of study on how to price goods in order to, so here in this case, the optimal price is a static price. If you knew that price, you would offer it all the time. So there has been work on how to learn this optimal price. There's also been work on if there is supply constraints, inventory constraints, then how do we learn a good way of pricing the goods over time? The next important set of models is where the demand model is not the same across time, but it depends on something called the context. Now, context is different from saying that the demand model is varying over time. It's not varying over time. It's still the same model, except that it depends on the context available at that time. So, for example, the demand could depend on the demand could depend on the characteristics of the hotel room that you're offering. So that hotel room's characteristic or the customer's characteristic, they are formulated as form of a feature vector, and the demand could depend on that. But how the demand depends on that feature vector does not vary over time. So given the same feature vector, given the same context, you always have the same demand model. Now, this is different from what we call non-stationary demand model, where across time, as we go along, as we make sequential decisions, the demand starts changing. The demand grid starts changing, and there has been some work on arbitrary but bounded variation in this demand. Our work differs from that in the sense that we consider not arbitrary variations in demand, but a very structured model of sequential variation. And this structured model can be described as a Markov model. And we will show, and this is in line with some work done by very recently, although very little work has been done in this kind of areas. There's a very nice survey by Denver from 2015, which surveys a lot of these models which have been traditionally popular in OR, but very little work has been done in terms of learning on them, at least theoretically. So if someone is interested, look at that survey, and you might even get ideas for more such problems that can be looked at. So coming to the model we consider here, so what is the aim of the model we are picking? So I would kind of suggest as a theme for the talk, not to focus so much on the particular model we are using, but to think about what we want to capture and what else can be captured using these ideas. So what we want to capture here in particular is what we call a word of mouth effects. And these are not something that we are studying for the first time. These have been considered like for decades in marketing. Word of mouth effects are considered very, very popular in terms of determining the demand of a product. So how we characterize these word of mouth, how we model them. So traditionally in the model we are going to consider, we think of two kinds of influences. So the first, so we call them external and internal influences. External influence refers to anything that is away, not about word of mouth. So it's about the brand image, about the perception of that product before even it's launched. So for example, if Apple is going to launch an iPhone, just from the perception of Apple, you have certain expectations about that product. Or because of the advertising done before the launch, you have certain expectations about that product, which will determine your response to the price point placed for that product. So all these factors we refer to as external or exogenous to our pricing process. What is internal or social effects are the effects that are what we call imitation effects. So what happens is once the product is launched, then depending on how it is perceived in the market, its perception changes, and people are influenced by each other socially and they might consider the product to be better than what they perceived earlier because a lot of other people are buying it, for example, or other people are reviewing it. And because of this, over time, as the product is launched, its demand changes. In particular, we see that popular product gets more popular because when people see other people buying them, they also want to buy it. So this gives a kind of a nonlinear growth in the adoption of a product. In particular, if we, so just to show this phenomena, we took two very different kind of spaces and show that this kind of phenomena exists across many domains. If you look at the traditional literature in marketing about diffusion models, you can see hundreds of domains very different from each other, all of them showing this kind of phenomena. So here we took Amazon data and Stack Overflow data. So on Amazon, we think about, since we didn't have the data on sales, we interpret the data on reviews, so number of reviews as being proportional to number of sales, because you can imagine that people write review only if they buy a product. So a fraction of those who buy a product write a review. So we think of growth in the number of reviews of a product as a substitute for the sales of the product. And we plot here with time, how many new reviews are we getting? And if there was no such popularity effect, then we would see a linear growth in the number of reviews. But here we see that as we, or even if the demand model was stationary, we would see a flat number of new reviews every time. But here we can see that the growth is non-linear over time. If you have initially a lot of reviews, then the number of reviews increases even faster. A very different space is Stack Overflow. Here we think about the same phenomena existing in number of answers to a particular question. In particular, you can imagine that any question that receives a lot of answers becomes popular and gets attention from other people, and then it receives even more answers. So you can see here, the good thing about Stack Overflow is that since it's much easier to respond to a question, we have much more data on this. So here we can get much more detailed curves. So different colors here show different category of questions because they have a different phenomena of diffusion. And you can see that initially every question launches in a different way. If a launch is good, if you get a lot of answers initially, then there is a nonlinear growth in the answers. And then over time, as the market saturates, as most of the people who like to answer have already answered, you will obviously see a decrease in the number of answers. But the curve that you follow depends really on how the initial launch happens. If it gets a lot of attention initially, then it really shoots up because of the imitation effects. So these phenomena are not new, as I was saying. These are very well known in marketing, due to which when people are deciding how to price a product, they decide a lot. They think about the life cycle of a product, which looks like a curved life cycle: initial lot of growth and then decline as the market saturates. And due to these understanding of this kind of life cycles, we have these common practices where we give like many companies give initial discounts, or some retailers even send free products to people who review them in order to get an initial boost in sales. And because they know that once you get an initial boost, the product gets some kind of word of mouth, then that will drive the sales even further later on. So this is a folklorish way of saying that the way we price products should take into account not just this kind of independent demand, but this kind of life cycle of a product, where you want to consider that once the product is launched, there will be other factors like social influence and imitation, which will decide how the demand evolves for that product. So how do we take these into account? And obviously, when we want to take into this account into learning, we want an analytical model that will capture these kind of effects. And luckily, we don't have to come up with a new model. These are well-studied models, studied in operations management and economics. And one of these models introduced in 1969 and arguably one of the most popular models in the revenue management literature or marketing literature is Bass diffusion model. So Bass diffusion model is a very, very simple model. In the original model doesn't talk about pricing. It only talks about how a product is adopted by the market once it is launched. So how does the two factors of external influence and internal influence, innovation and imitation, affect its adoption? So the scale of this the market in this model is characterized by two things, which is market size and time horizon. And later on, we will see how important it is to distinguish between these two measures of scale. So traditionally in bandits, in the talks you would have seen, mostly we think only about the time. But here, it's also important to think about the number of potential buyers, which is the total market size. So given the market size and time horizon, the model is characterized by two parameters. We call them alpha and beta, and they refer to coefficient of innovation and coefficient of imitation. And these are just the name, but you'll see why the intuition of why we are calling them that. So given these two parameters, alpha and beta, the market model is simple. First, let me describe as the intuition of how the market is formulated, and then we can discuss the differential equation. So the idea is that we think of in this market, the likelihood of a buyer who hasn't yet bought a product to buy the product FT, given that they have not already bought, is simply a linear function of those who have already bought. So let's just examine this. So if we did not consider imitation effect, then so if we didn't have this term, no social influence, then it would simply be something like an independent demand model. So we would simply say that likelihood of somebody to buy a product given that they have not already bought is fixed. It's always alpha. But if we consider a social influence effect, then we are saying that the likelihood of a buyer to buy is alpha, but it's also proportional. There's also a factor proportional to how many have already bought. So if a lot of people have already bought, then you're more likely to buy it because you're affected by the popularity of the product. In differential equation terms, which is mainly the model we will use, we say that if XT is the fraction of market already captured, XT is between 0 and 1, then the change in the market capture is equal to alpha plus beta times XT. So this is the innovation plus imitation effect, times the fraction of the market not yet captured. So what proportion of the market will be captured instantaneously is alpha, the part is the fixed part, plus beta times XT. Now, this is the main model of how the market will be captured. So how the adoption will evolve over time. This still does not have pricing, and we will introduce pricing next. And here on the right, just as a straw man check, we check if this model is a good fit for the two examples we considered earlier. So here in the first graph, we are going to, we fit the Bass model, this dashed line over here, to the Amazon data. And you can see that even though the curve looks very different from Stack Overflow, there is actually a parameter for the model for which this fits well. And here we fit the same model to the Stack Overflow data. And you can see, since we have more data, you get a much better fit here. So before I take questions, let me just finally introduce the Bass model with pricing decisions. So as I said, the original model introduced by Frank Bass in 1969 does not actually have any pricing aspect. It only thinks about once a product is launched, how does the demand evolve? But since we have a control of price, we also want to think about how does the price play a role in this evolution. So one model in order to capture the price effect was introduced by Robinson and Lakhani in their management science paper in 1975. And here they say that we can think of price as having an effect on both the innovation and the imitation effect. So they model simply as if we have a price PT at time t, then at that time, both these coefficients decrease by a factor of e raised to minus pt. So this is just a model, and I think the most important assumption they are making here is not so much about the exponential function. Think of this as some decreasing function in price. But one important modeling assumption they are making here is that the price affects both the imitation and innovation effects in the same way. So they're both affected by a factor of e raised to minus pt. Now you can say that, well, that's not really true. Why would the imitation be affected by price? It could be that the price, more expensive products have more imitation effects or less imitation effects compared to the less expensive products or not. But this, any model is questionable, and you should think about what can be the other models which would capture the price effects better along with the diffusion. Okay, but right now, given the history of work on these kind of models and the studies on these kind of models, we will stick with this model for now. Now, given this pricing model, now we have a full decision-making problem, right? So the decision-making problem is can be thought of as a Markov decision process, although it's a continuous state and action process. So we have a continuous time horizons from 0 to t. And every time t, we can see the fraction of market captured so far. So we know that how much market has been captured because we know how much sales we have done so far and what was the full market size. So given the state of the market in terms of market capture, we can offer a new price. And given the price and given the market captured so far, this is how we will see the market, the new market capture, the new adoption, the new sales. So then our reward in that small infinitesimal time interval, because we are in a continuous time model, it will be given that the price we offer times the amount of adoptions we see. So dxt is the infinitesimal adoptions we see in the infinitesimal time times m, the market size. So the total revenue which we want to optimize ultimately is given by this expression, price times the market adoption over the time horizon. So the goal here is to decide a pricing policy. So decide at every time t what price to offer in order to optimize the total revenue. Of course, so far there is no uncertainty here, there is no learning, and that's what we are going to do next. We're going to introduce noise in this model, and then think about how to learn a pricing policy. Okay. And before we go there, let me just say one more thing about the deterministic model without the noise. That deterministic model, in fact, has been solved. So we do know what the optimal policy for that model is. And it's kind of illustrative to look at that because it's so different from the way we think about pricing in a stationary demand model. In a stationary demand model, if you have no supply constraints, then the optimal price is a fixed price. It's a fixed price point that balances the revenue with the demand. Okay, so so if you think of price as a nonlinear price response demand model as a nonlinear function, it's the optimal point on that curve. But here, even without any supply constraints or budget constraints, there is a nonlinear pricing policy, and that matches this intuition that we presented earlier, where we want to give some discounts initially in order for it to launch. And then kind of when the market saturates, we want to offer lower price so that more of the remaining market will be captured. So if you see at what the pricing policy looks like, it really depends on what beta versus alpha is. So here, if beta is 0, as I was explaining earlier, if you remove this basically says that every time you offer a price, the market capture is a fixed portion of the remaining market. So this means that as we go along, the demand will just decrease because more and more market gets saturated, this part decreases, so there will be less and less adoption. So if beta is small, then we know that market is getting captured. You only get a fixed proportion of market, so you should decrease the price. As more and more people start buying a phone, and most of the people who were going to buy it have already bought it. The phone is old, it's not that attractive anymore because market is saturated. You want to decrease the price and get squeeze the remaining market as much as you can. But if beta is much, much larger than alpha, the curve becomes the pricing policy completely changes, because now you want to think about the imitation effects more than the actual innovation effects. So you want to think about the popularity. Can we make the product go viral? To do that, you actually want to launch at a relatively lower price point, and so that it gets some initial adoption. And as it becomes popular, you can raise the price. Now, this consideration also changes with how long time you have. If you don't have much time, if a next version of the phone is going to come soon, you don't have that much time, you can just increase. You don't worry about saturating the market at all. You can just increase the price as the phone becomes popular. But if you have a lot of time, then at some point the popularity will start waning and the market gets saturated. Then you want to decrease the price. So I wanted to illustrate these curves just to show you that even without any noise in the process, if you even know the model, finding an optimal policy in this market is not trivial. And you actually want to have a non-trivial, non-stationary pricing policy in order to match the life cycle of a product, which is non-linear. So our goal will be to think about how can we learn such a pricing policy, non-stationary pricing policy, from data. As we price, we see the response, and we want to learn the demand model and figure out this pricing policy. So to do that, formally, we have to first introduce a noise. And this is kind of our noise model, although it's very much based in how usually in the literature they had put the noise model in pricing problems. So we simply say that we will use the same model for transition. So in expectation, the number of new adoptions is given by the same model as we had here, except that the actual number of adoption is a Poisson process with that expectation. So that's all we are doing. So we're just introducing a Poisson model in order to introduce noise in this process. So what we observe is the actual sales in every time unit. So actual number of actual adoption rate at every time step. And this is a noisy version of the real true model. And our goal will be to use these observations of actual sales in order to learn the unknown model parameters, alpha and beta, in order to find the optimal price for the true price policy for the true model. So that's in the nutshell the description of the problem. And let me pause for a minute to see if there are pressing questions about the model.
So Shipra, you're doing this in continuous time. So at what times will you change prices? Will it be at discrete times?
So that's a very good question. So in general, we allow you to change price at any point you want. I think what it makes sense is that you only change price if after some new customer comes. So we are thinking not in terms of price, but in terms of customers, right? So the customers can come at any time. And you might want to change the price in practice only at these times, right? But in general, the problem allows you to change price at any time. Our algorithm will only change it a few times.
All right.
And in the lower bound, actually, we assume that you don't change prices in between arrivals. Yeah.
So potentially you could allow changing of prices at any time, and then you'll get slightly different results. Okay.
So if you allow changing price any time, then our lower bound doesn't hold. Our lower bound holds for any process that changes time only at arrival points, that changes price only at arrival points. But the original problem allows you to change price anytime.
Okay. Any other questions? Yeah, I guess we can go ahead.
You're right. Yeah. So now given this problem, we want to do something like what we do in most learning problems. We want to maximize total revenue and we want to measure regret. And regret here is slightly different from what we see in learning. We are not really talking about comparing to a best fixed price or best stationary policy. Regret is really just a different, we are using it as a name for error. So we are just saying, suppose opt-T is the optimal expected revenue of the best stochastic policy if you knew the model, right? So best clairvoyant policy. So everything you can do if you know the model in expectation, whatever you can do, compared to the revenue we obtain. So it's really the difference, the suboptimality of our algorithm. And we show that our algorithm will get you a regret bound. And let's look at this a little bit. So here, all I'm eliminating is some factors in log m and some constants that depends on alpha and beta. And I'll give you the exact regret bound later. But what is important to note here is the dependence on m is the more important part than the dependence on time. So we will see later, even in the lower bound, so we'll give a matching lower bound, showing this is the best you can do. We will show that this is the best you can do. And so what happens here is that the market size is the main determinant of the complexity of this problem. So if the market size is large versus market size is small, really determines how you should behave, because time, as I say, it's a continuous time process. You just adjust to the time. But market size is the total revenue, determines the total revenue you can get. So scale of the problem is more depending on the market size than the time. So in order to describe the algorithm we are using, there's a key property that we use, that we prove and we use both to find the algorithm and to do the analysis. So this key property is that we observe, and this is not something, if people who are familiar with online optimization with budget or constrained online optimization might have seen something like that before. But it is much harder to show that here because of the MDP involved. So basically, we show that a concavity property, meaning that the value of this, basically the revenue at any given, starting from any given state of the market, so the total best revenue you can get starting from any given state of the market in the deterministic setting is concave in the adoption level, meaning the state in the state. So if I tell you X is the current fraction of the market capture, so that's the state of the market right now, and I compute the optimal revenue that you can get starting from this point, then the value, that value is concave in this X. And why is that important? Because we can use this to show that the optimal stochastic revenue in the noisy process is actually upper bounded by the deterministic revenue. And this is simply doing something like just using Jensen's inequality. So you would say if these are all stochastic paths, then the expected value on the stochastic is smaller than the deterministic revenue on the expected path. So it's simply a use of Jensen's inequality. And the implication that I'm pointing to is to say that our goal, which was this expected total revenue of the optimal non-stationary policy, so the gold standard, is actually smaller than the optimal revenue of the deterministic problem. And why is this useful? So we get two insights from this. First of all, we get some handle on how we can analyze regret, because we can just replace and upper bound this regret by replacing this objective, which we don't even know. We don't know what the optimal stochastic non-stationary policy is, but we do know what optimal deterministic policy is, because that has been solved in the literature in the past. So we can upper bound the regret by the difference from our revenue to the optimal deterministic revenue. And the other insight we get is that since this is so much better than this, one way to design the algorithm is to estimate the model parameters and then find the deterministic policy, optimal deterministic models policy to for the estimated parameters and run that policy. And hopefully the revenue we get will be good enough compared to this. Okay, so with these two insights, this is the algorithm we use. We basically do a very simple parameter estimation and optimization process with a little bit of UCB ideas, the upper confidence bound ideas. So we simply use an exploration price. So this exploration price, you can even set it to be 0, or it's just has to be set to be low enough. But because what we want to do with this price is that we want to eliminate this part of the model and just observe this part of the model. So even if you set price to be 0, that's fine. We want to observe this part of the model. So if we set price to be very low, we observe the alpha beta part of the model. We observe the demand from that part. And we can use that to estimate the alpha beta model, alpha beta parameters. So what we do is we offer this very low price, but not for a fixed time. So we are not thinking in terms of time, but we are thinking in terms of market. So the time is fixed, but we offer this exploration price until we observe some m raised to 2 by 3 customers adopt the product. Okay, so a sublinear fraction of the market is adopted the product. So once we have adopted this, once we have that many adoptions, we stop, we estimate our alpha. Now we could also estimate beta from here, but beta unfortunately needs more samples than that. Why is that? Because the estimation of beta is much more difficult, because estimation of beta is kind of censored by how much fraction of market we already have adopted. So intuitively think about, in order to observe social influence effect, you actually need to already have some penetration of the product, some diffusion. If nobody has bought the product, how will they even talk about it? You cannot observe word of mouth effect without people having already adopted it. So how it shows up in the model is that the effect of beta is not observed directly. We only observe beta times xt. So if xt is small, you're not going to be able to estimate beta very well. So because of that, we cannot just estimate beta after observing m raised to 2 by 3 adoptions. We have to update beta to get better and better estimates of beta when we observe more and more adoptions. So to do that, we will have to update our estimation of beta as we see more adoptions, and we do this using a doubling time interval kind of trick, except that we double the number of customers. So every time we double the number of customers, we re-estimate beta by offering the exploration price. Now, what do we do with these estimations of beta and alpha? So estimations are simply, you just fit the parameters to the model. Now, what do we do with these estimations? So once we have these estimations, we can compute the confidence regions on these estimated parameters. And the price we will offer will be a lower confidence bound. So we will offer a lower price than what we think the real optimal price is. So why we want to do that is, by offering a lower price, we are ensuring that we can observe as much market, we can get as many adoptions as the optimal price. So we want to eliminate one side of uncertainty. So we want to make sure that we get as much of market capture as the optimal price, but maybe at a lower price point. So we will not get as much revenue as the optimal, but we get as much market capture. And why is that useful is that because if we get as much market capture, all we have to bound is how much revenue we are losing by offering a lower price. We don't have to worry about the fact that we don't even have that much market, so we don't even have that much samples and so on. So this is the whole algorithm. We basically offer an exploration price whenever we double the number of customers, and this exploration, the observations from that period of exploration is used to estimate the alpha beta parameters. We offer a lower confidence bound on the price, and we observe the demand, we collect the data, and we keep going. And for this algorithm, we show the regret bound that I mentioned earlier, which is dependent on m as m raised to 2 by 3 and logarithmically on time. And in order to discuss the importance of these two features, let me also mention the lower bound. Okay, so what happens here is that in this problem, the interaction between M and T is very important. So the market size and the time horizon. So if the time horizon, in fact, we can show that the lower bound, the difficult cases of this problem come when the time is basically a constant. So it's this particular value. And for this time horizon, the market capture is roughly equal to M. For any time horizon that's much larger than this, you capture, it's easy to capture almost all the market. So you don't really need to optimize price that much. If the time horizon is smaller than this, then anyway you cannot capture the full market. So this regret bound will be meaningless. So this is more formalized in our lower bound. So what we can show is that if you fix any alpha beta, so it's not a worst case lower bound, we can show there are infinitely many markets with this kind of lower bound. So you give me any alpha beta, I'll find you a market very close to that alpha beta where this lower bound holds. So for any alpha beta, if you have a time horizon that's theta of 1 over alpha plus beta, then we can show there exists a market with alpha beta parameters very close to this alpha beta, where the regret for any algorithm is at least m raised to 2 by 3 order in terms of market size. And just a caveat, by any algorithm, we mean algorithms with certain restrictions. So the first restriction is that we need price to be upper bounded in this market by logarithmic of t. And in fact, you can show that deterministic optimal price satisfies this constraint. So any algorithm which has bounded price like this, and any algorithm that doesn't change price between custom arrivals. So I believe this second constraint is more technical. We had some issues with analyzing if we allow changes, arbitrary changes at any time step. But the first constraint, I believe, is necessary. So given an algorithm, given a pricing policy satisfying these two restrictions, we can show that the algorithm cannot get better regret than what we have shown. And our algorithm, of course, satisfies these two restrictions. So I don't think I have, how much time do I have? Can you tell me?
Maybe a few minutes.
Yeah. So I don't want to go into the details of how we prove these bounds. Just want to summarize what we have done. So basically, we look at this new model called Bass diffusion model. And really about what I want to get across from this talk is this idea that when we think about dynamic pricing, can we think about models where the impact of a price doesn't remain the same over time? Because this is in fact well known in the industry. So in the industry, when we decide a price point of a product, we do not think of we think of the life cycle of a product, right? So and we may not, so in practice, we may not change the price over time, but effective change might be done through discounts. So you might offer some discounts initially, or later on when the market gets saturated, you might have some promotions. So there are a lot of ways to implement these non-stationary pricing policies. Doesn't have to be actually changing the price. It could be change in advertising. It could be change in the promotions or discounts. But overall, we always think about how to capture the market over time rather than thinking about what will be the response to a price point. So at least for some domains, maybe some domains we can still think about stationary demand, but many domains we think about this kind of life cycle of a product. And Bass diffusion model is kind of a starting point to capture these kind of demand models. And there is so much more work that can be done by having more complex models, maybe more contextual models of how this demand evolves using a diffusion model. What we considered here was a simple Bayes diffusion model for 2 parameters for one product. And there is work to be done in terms of how to expand this to multiple products with features and customization. So if I would be really happy to answer questions and also any discussion on how we can take this forward to multiple products, to context, and so on. Thank you.
Questions? Okay, it's been a long day. I have some questions.
Yeah.
So how do you construct these confidence regions? And then if instead of LCB, you use something else in that region, would you really suffer? Or?
Well, so the issue is like if you don't use the lower confidence bound, like so the first part of the question. So we constructed really using standard machine learning based concentration bounds, because what we are doing is when we say like update beta hat, alpha hat, we are literally just fitting we have a model and you're fitting the model parameters, right? So you can get the typical bounds on how much the error will be, generalization bounds basically, and that will allow you to construct a confidence region with high probability. So there's nothing like very complex going on here in that sense. The lower confidence bound, the more important part there is that the problem there is that if you don't have a lower price, if you have a higher price, it's hard to know how much opportunity you will lose, because over time you might lose a lot because it's a non-linear curve. So if instead of riding this curve in terms of adoption, if you're riding this curve, you could lose a lot of demand. So offering a lower price makes sure, at least in terms of number of adoptions, you are riding a higher curve. Then you only need to bound how much actual revenue you lose. So it could become unbound. Yeah.
But can you prove that if you use upper confidence bound, you'll be worse off? Mathematically, can you say something?
So we cannot show a lower bound like that, but I can tell you that intuitively, I think you can lose like linear because of this. Because if you use a higher price, you lose the opportunity, like you lose the customers.
Right.
And that curve is non-linear.
Okay. Okay. Any other questions? Let me give the mic.
For the price transition. Can you hear me?
Yeah.
How did you arrive the transition point m to the power 2 by 3 for the price? Is it analytical value or you
this one?
Yeah, m2 by 3.
Yeah. So basically, yeah, if I had time to go to the lower bound proof, I could have explained this earlier. But basically, you can say that. So if you think about bandits, there we have a lower bound saying that in order to distinguish between mu versus mu plus epsilon, you need square root m, like just information theoretically, like KL divergence based proof, you need square root m samples, right? If epsilon is a constant. So in order to distinguish between a market within constant error, you need square root m samples, order square root m samples. Now here, what happens is because of this, so if you only had alpha, I would need square root m. But if you have beta x, which is where the effect of beta is affected by how much you already have, then you actually, in order to distinguish between two different market parameters, you need m raised to 2 by 3 samples. That's what we use to determine how many customers we need to wait before we estimate.
Okay, thanks. The other question you consider, it's Poisson arrival, right? So does it mean it is somehow related to the classical queuing system of finite customer or something?
Not queuing, but Poisson is the reason we use Poisson. So Poisson is very popular in pricing also, like almost most of the time, at least in revenue management literature, people use Poisson to model demand. And the reason is because Poisson allows the scale of the noise to depend on the scale of the actual expectation, right? So in Poisson, the noise is not fixed, right? It depends on this value. So it's not like you will always have a noise of standard deviation 10, whereas the actual value actual expectation could be 0.1 or 0.7. Okay, so it allows the scale of the noise to vary with the model parameter scale. So and Poisson is kind of standard in this. You could consider other models, but we tried a different noise models. The problem is if you make the noise variation to be a different parameter than the expectation, a different scale, then it's hard to say what is the meaningful scale of the noise.
Okay, one more question. So suppose we are not able to reach the market coverage in our horizon T, whatever is well defined earlier. So in that case, we are being penalized, right? So do we have any trade-off that we should increase the horizon so that the penalty will be minimum, or it is better to have the well-defined horizon, whatever we have at earlier?
Yeah, that's a good question. That's a choice of like what kind of setting you want to consider. Here we assume that the horizon is something being given to us by the problem, right? So if you have 3 months, you have 3 months, right? But you're right that in practice, these things may not be fixed in advance. Market size might be fixed, but there might be some flexibility in time. And you might on the fly say, well, I need some more time. Maybe I can keep this product in the market for longer. But I would say that's more of a question of the original like revenue management / marketing problem rather than learning problem. So I think learning problem is just following the setting you want to decide for your revenue management problem.
Okay, all right, thank you.
Thank you.
Okay, so if there are no more questions, we'll call it the end of the day, and we'll thank the speaker once again. Thank you, Shipra, for making time.
Thank you everyone for attending. Thank you. Bye.
Bye-bye.